Hello students, now we are going to study about depression in freezing point, another colligative property, third colligative property. As I already told what are colligative properties, we know colligative properties of the solutions are those properties which depends on the number of particles and not the nature of the particles. We'll see what is depression in freezing point, we'll see how does it depends on number of particles and why it is colligative property, and we also determine the formula for the molar mass of the solute from this colligative property, as we have seen in elevation in boiling point and relative lowering in vapor pressure. So let us see what is freezing. What actually freezing? When a solid gets converted to liquid, this is what? Fusion. This process is called as fusion or melting. This physical change is called as fusion or melting. But when liquid solidifies and forms a solid, it is called as freezing or solidification. The two physical changes I discussed, solid converting to liquid is known as melting, and liquid converting to solid, a back process called as freezing. Now a solution freezes when its vapor pressure becomes equal to vapor pressure of pure solid solvent. When a solution freezes, when vapor pressure of solution becomes equal to vapor pressure of pure solid solvent. When this occurs, then solution freezes. Solution freezes when vapor pressure of solution becomes equal to vapor pressure of solid solvent, then solution freezes. First of all, this is known as freezing. Now we will see what is freezing point. Now freezing point is the temperature at which solid and liquid phase of substance in the solution have same vapor pressure of solid phase of same substance, solid phase, is equal to vapor pressure of liquid phase of the same substance. Then that temperature is known as freezing point. Temperature at which vapor pressure of solid phase becomes equal to vapor pressure of liquid phase of that substance, then temperature is called as freezing point. That temperature is called as freezing point. The two important things before we should understand before discussing depression in freezing point, that solid gets converted to liquid. This physical change is known as melting or fusion. The temperature at which melting occurs, that is known as melting point. Now we'll find that liquid gets converted to solid. This is known as solidification or freezing. But when freezing takes place, whenever vapor pressure of solution becomes equal to vapor pressure of pure solid solvent, then we will find that solution freezes. Now temperature at which vapor pressure of solid phase and vapor pressure of liquid phase become equal, then that temperature is called as freezing point. These two things we must understand before starting this. Now, why depression in freezing point take place? Let us see. Depression in freezing point, whenever non-volatile solute is added to a liquid solvent, a liquid solution is formed. Now this liquid solution contains the non-volatile solute, and we know vapor pressure of such solution, containing non-volatile solute decreases, is lesser than vapor pressure of pure solvent. If vapor pressure decreases, so we will find that the substance freezes at lower temperature. Since vapor pressure of solution decreases, then freezing point will also decrease. If vapor pressure increases, then we will find that there will be elevation in boiling point, but there will be depression in the freezing point. If we see that freezing point of solution decreases, so hence freezing point of solution will be smaller than freezing point of solvent, pure solvent. Thus, we will see there is a decrease in the freezing point on adding non-volatile solute. Just once again, whenever non-volatile solute is added to a liquid solvent, liquid solution is formed. Vapor pressure of such solution will decrease, and since vapor pressure decreases, there will be decrease in the boiling point. Hence, boiling point of solution will be lesser than the boiling point of pure solvent. So, there is a depression in the freezing point on adding non-volatile solute. Let's see mathematically this colligative property. Let's TF is the freezing point of solution, and TF naught is freezing point of pure solvent. We will find TF is more than TF naught will be more than TF. So therefore TF naught minus TF will be equals to del TF. Depression in freezing point is what? TF naught minus TF. This is one of the expression for depression in freezing point. Del TF is depression in freezing point. Depression means घटना, decrease होना in freezing point. So whenever non-volatile solute is added, there will occur depression in freezing point. Now if we will see graphically, here vapor pressure is plotted against freezing point, that is temperature. A little lower. Freezing point that is T. We'll see that a curve for liquid solvent, this is frozen solvent, this is the curve for frozen solvent this side, this is the curve for liquid solvent. A little higher, it will be a little higher. This curve is for liquid solvent. Just now where the vapor pressure of frozen solvent and liquid solvent is equals, that temperature is freezing point. This temperature is freezing point of solvent, pure solvent, TF0. Now for solution, we'll see when we add non-volatile solute, the curve becomes like this. The curve becomes like this. This is the temperature where your solution freezes. So this is the value for del TF, depression in freezing point. So curve ABC is for solvent and curve ADE is for your solution. So this notch in the curve shows where the vapor pressure of frozen solvent and liquid solvent becomes equal. This notch shows D point where the vapor pressure of frozen solution and liquid solution is same. So here we will frozen solvent and solution becomes equal. Initially I told a solution freezes when vapor pressure of solution becomes equal to vapor pressure of the solid solvent, that is frozen solvent. So this is the TF, this is TF0 and the difference will be del TF. So what is depression in freezing point? On adding non-volatile solute, we will find there is a decrease in the vapor pressure. This results in decrease in the freezing point of the solution. Hence, this is known as depression in freezing point. It occurs due to lowering in vapor pressure on addition of non-volatile solute. Now we will see how it is a colligative property. Let's see how it is a colligative property. Del TF again is directly proportional to molality. M is molality of the solution. Molality is the number of moles of solute dissolved in 1 kg of the solvent. So del TF is directly proportional to molality, and this we will see del TF equals to KFM. This KF is what? Cryoscopic constant. It is cryoscopic constant or molar freezing point constant. molar freezing point constant. It is also called as molar depression constant. These expressions are very important for numericals. So we'll find del TF when M is 1 mole per kg, that is if we have solution 1 molar, then del TF is equals to Kf. How we will define cryoscopic constant? It is equals to depression in freezing point when we have solution 1 molar. When we have 1 molar solution, that is solution containing 1 mole of non-volatile solute dissolved in 1 kg of the solvent. So cryoscopic constant is defined as the depression in freezing point when we have 1 molar solution. Now we will see how it is colligative property. Since del TF equals to KFM, M is number of moles dissolved in 1 kg of solvent. Now I am putting equation number 1. Putting this value of M. Now see, since del TF depression in freezing point depends on molality, and molality depends on number of moles of solute. So number of moles of solute, that is number of particles of solute. Since del TF depends on molality, which depends on number of moles of solute, hence it is a colligative property. Hence depression in freezing point is colligative property. Now we will determine the molar mass from the depression in freezing point, as we had seen for other two colligative properties. Determination of molar mass of solute from depression in freezing point. We will derive formula for molar mass. Let us see, it's not difficult as you had done two other colligative properties. Let's see. Del TF is equals to KFM. This is one. Now since M equals to number of moles upon given mass 1 kg of the solvent. Putting this value in above expression, we will get del TF equals to KF NB upon WA into 1000. Now we will see NB equals to, since NB equals to WB upon MB. Always I say, you remember number of moles equals to given mass upon molar mass. So putting this is another expression. del TF equals to KF WB upon MB into WA into 1000. This is third expression. This is one expression useful in our numericals. You can use this expression also for numericals. If number of moles are known. If number of moles are not known but mass are given, then you can go for this third expression. Now from here we will cross multiply. MB equals to KF WB into 1000 upon del TF upon WA. This is the expression for molar mass. If you want to find out molar mass, you can use directly fourth expression. We know del TF equals to TF not minus TF. We will see MB equals to KF WB into 1000 on putting instead of TF not minus TF, we can use this formula also directly. This is expression number 5. So we determined molar mass from this. We had seen del TF equals to KFM. On putting the expression of molality NB upon WA into 1000, we will get del TF KF into NB into 1000 upon WA. We know NB equals to given mass upon molar mass, that is WB upon MB. On putting this expression, we will get del TF KF WB into 1000 upon MB into WA. Just cross multiplied, we get this expression. On putting the value of del TF as TF not minus TF, we got this expression. So whatever values are given in our numericals, accordingly we can use the formulae. Here your third colligative property, that is depression in freezing point, is also over. We had seen what is depression in freezing point, why it is colligative property, and also we have seen how can we find out molar mass from the value of the depression in freezing point. We'll see osmotic pressure as colligative property in our next lecture. Thank you.